biochemistry. They are saturated hydrocarbons. We'll get to this terminology. How do I get to my next slide? Historically, compounds from living systems, plants and animals. Organic, I mean, you go into HEB right now and organic has the connotation of natural, doesn't it? It's kind of interesting because in chemistry, organic chemists are making not natural, but synthetic molecules. Organic chemists typically are making molecules that are not natural. I think I mentioned on Monday aspirin, that it starts with salicylic acid, which is natural, and then they modify it and make a compound you can't find in nature, aspirin. So organic chemists are oftentimes, that's what they are doing. They're making molecules based on carbon. Carbon is pretty much at the center or the critical element in an organic compound. And there's other things there. There could be hydrogen, oxygen, nitrogen. There can be other things there. But there's always carbon. Carbon is kind of the backbone of the molecule. But it got that name because it was believed back in the late 1800s that only living things could make these kinds of molecules. Even just simple little organic compounds that they extracted from nature, sugar, glucose. They say, oh, the only way you can make glucose is plants can make glucose. It has to be living to make these molecules. And then finally one guy made a simple urea, a simple organic compound. And he said, I made this in the laboratory. And he was laughed off the stage and, I really made this. I made it from scratch. I didn't, some bacteria got in there, or something happened to make it, because we can't make these molecules. And then more people did it and made it and said, oh, we can actually produce these organic molecules. So that they got this name, meaning living, but now today the connotation is synthetic. Pharmaceutical drugs are not typically what you find in nature. It's what some pharmaceutical company has made based on carbon. So that's where this word comes from. Study of carbon compounds. The exceptions, simple carbon compounds like carbon monoxide and carbon dioxide, about the only two that come to mind that we got carbon in them, but we can't do with them what we can do with organic other carbon-based molecules. They're done. They've been completely oxidized. This one hasn't yet. That's the completely oxidized form of carbon. This is partially oxidized. This is poisonous. This will suffocate you. So I'd rather have this around than this around, because you just get out into the oxygen and you can breathe again. This stuff here is actually poison. Cyanide. Okay, cyanide. That's the other one. Good thing I got on my slide. So if you had something like sodium cyanide, that's carbon-based. CN group is the cyanide anion, but that's kind of in the realm of inorganic chemistry. But everything else with carbon is pretty much in the realm of organic. And I mentioned on Monday again that biochemistry is predominantly organic molecules. They're a little bit more complicated than just simple methane or propane or octane. But they are naturally occurring molecules that are biologically active. They do something in living systems, like glucose. Organic chemistry is all around us. Where do we get methane and propane and octane? What else do they have in common? What What is their source? Where do they come from? Petroleum. Yeah. Crude oil. So you take crude oil and you can boil out of it. I mean, usually where you find oil, you find methane accumulating above it. So you go in, when they're drilling for oil, the very first thing they find is gas. Is that what you used to do? And were you drilling for oil or for gas?
I was blowing up the sediment.
Okay, breaking it up to get in there.
Breaking up the rock, and then someone else came and sucked up the
Okay. The oil or the gas. Yeah. So this stuff accumulates above it's in the crude oil, but it's coming out of solution, and it's got a higher vapor pressure, and it just accumulates above the crude oil. So clothing, here are some natural fibers: silk, linen, wool, cotton. Some synthetic fibers: Stacron, nylon, Orlon. All right, so you can't find nylon in nature, but it's a synthetic fiber. Plastics, pharmaceuticals, pesticides, gasoline and oils. The organic chemistry and organic chemicals are all around us. Okay. You don't need to know all of this for this quiz in a few days on alkanes. You need to know this, alkanes, what they are. But I want to just sweep down through these different classes of organic compounds. And we are going to study all of them eventually. Chapters 10 through 15. So this is chapter 10, alkanes, and alkyl halides, and that's an alkane with a halogen. X equals fluorine, chlorine, bromine, or iodine, an iodide, on a carbon would be an alkyl halide. So that's about as far we'll get with chapter 10. Chapter 11, so then we're going to start focusing on what is the functional group? What is the unique aspect of the structure of this class that ends up lending a lot to its properties? So we get into alkenes, alkynes. I don't know why that isn't in there. Alkynes and aromatics is the focus of chapter 11. And alkenes have double bonds, alkynes have triple bonds. Aromatics are double bonds, but in a ring. Okay? Really, right now, the purpose of this is just to introduce this to you, so don't feel like I got to run home and memorize all these. Okay? When we get to chapter 11, you'll become familiar with it. I look at these chapter 10 through 15. You know the adage: how do you eat an elephant? How do you eat an elephant? One bite at a time. Okay? So don't just try to digest all this by Monday. You'll get indigestion. Okay? I don't want you to get indigestion. We're going to try to chew on this one chapter at a time. So, but that's chapter 11. You get into double bonds. They react differently. They're very much more versatile in their chemical reactions than alkanes. So we don't just burn these. Sometimes we do burn them, but we can do a lot of other things with these other than burn them. That's why we're burning those up there. So we can't do much with those, but burn them. All right, so then I don't know why this slide has these blanks in here. This stuff is supposed to say this. Chapter 12, alcohols and ethers, and it also mentions thiols, something else. Alcohols, ethers, thiols, and phenol, which is an aromatic alcohol. But Okay, the functionality here that we're going to see is an OH group. That's what makes it an alcohol. A COC bond. You got an oxygen in here, but not with an OH on it, just another carbon. That's an ether. So you can see chapter 10 and 11, all we're talking about is carbon and hydrogen, and maybe a halogen now and then. Chapter 12, we're talking about carbon, hydrogen, and oxygen. And then you get to chapter 13. Again, we're looking at, we've got an oxygen here, but it's a double bonded oxygen. Say that makes a big difference? Yeah, that's an aldehyde. And a ketone has a double bonded oxygen. What's the difference between these two? This one has it on the end of the molecule. This one has it somewhere in the middle of the molecule. They both have a carbon-oxygen double bond. So they do have some similarities in the way they react and what they produce when they react, and some differences. So they fall into their own class, aldehydes and ketones. Then we get the carboxylic acids, which has two oxygens, a carbon-oxygen double bond and a carbon-OH single bond. That's a carboxylic acid. As we mentioned, vinegar has acetic acid in it. Apples have adipic acid. There's malic acid. There's lactic acid. There are a bunch of different carboxylic acids. They all have that functional group on them somewhere, maybe two. But they all have that functionality. That's what we mean by a functional group. How does that function? Well, we'll learn that when we get to chapter 14.
So the carboxylic acid, they have two double bonds?
One. They have one carbon-oxygen double bond and a carbon-OH bond. Yeah, there's only one. Like I said, there can be two of these carboxyl groups on the same molecule, but they will at least have one of these functional groups somewhere on the molecule, and it's carboxylic acid. And an ester kind of fits in here. Why does it fit in here? The ester, you take off that hydrogen and you put another carbon compound in there, and you have an ester. So there, you can see some similarity here. You got this, but a carboxylic acid has that hydrogen, that makes it acidic. An ester does not have a hydrogen there, and they're not acidic. That's esters. And then you get to amines. Some gremlin got into my slides and he erased some of this stuff. I don't know. Sometimes I do things by accident, and it take me an hour to figure out how to do it deliberately. But I don't know what happened here. So amines, we now come to our third element, nitrogen. That's an amine and an amide. We're going to have, let me see here. I better put it down here. We're going to have a carbon-oxygen double bond and a nitrogen, and that's an amide. You see, both amines and amides have introduced nitrogen. And I mean, right now, we could deal with 1,000 different molecules that piece them out into all these different things. So the purpose of this is just to give you an idea of what chapter 10, 11, 12, 13, and 14 are all about, and 15, and that we will get to them one by one. I don't want to overwhelm you. I think you could, if we tried to sit on this too long, it would get confusing. But if we focus on one class, simple class, probably the simplest, and get our arms around it and walk on into chapter 11, and then those are going to make a little more sense. Now you're just kind of adding, expanding your knowledge one chapter at a time. Okay? So that's, oh, here it is, all filled in. Beautiful. The gremlin left. All right, so you got it both ways. All right, so now let's come back to where we want to start here. Hydrocarbons. Carbon and hydrogen. That's all we're saying here. Hydrocarbons. The only two elements generally in there is going to be carbon and hydrogen. And this is chapter 10. And this is chapter 11. So hydrocarbons are going to break up into two categories. Saturated hydrocarbons. Chapter 10. Chapter 11, unsaturated hydrocarbons. A saturated hydrocarbon is one in which all of the carbons have single bonds around them. And they'll have 4 single bonds around them. Look at this carbon. These are bonds. 1, 2, 3, 4 bonds around that carbon. This carbon, 1, 2, 3, 4 bonds around that carbon. Well, let me see here. Single bonds. We get into chapter 11 and we're going to see double and triple bonds and conjugated double bonds. So this is not a single bond. There's a carbon-carbon double bond. They're sharing 4 electrons. Carbon-carbon triple bond. Those two carbons are sharing in a covalent bonding manner 6 electrons between them. All right? In chapter 10 under alkanes, you're not going to see that functionality. It's going to be single bonds everywhere. That means it's saturated. These are unsaturated. They one way, shape, or form want to break those bonds and form with something else. And so when they have the opportunity to do that, they do that. They're a little more reactive than our alkanes. So now as we move on, we're going to be focusing just right here today for chapter 10, alkanes, saturated hydrocarbons. That's also what the quiz will be on. Don't get confused. You don't need to study too much. What you need to study thoroughly are alkanes. So let's see what they're all about. Organic compounds in which the carbon is bonded to 4 other atoms by single bonds. There are no double or triple bonds. The simplest 2-word definition of these things are saturated hydrocarbons. We got a general formula. CnH2n plus 2. Now let me put these formulas here. So this is the formula. This is the molecular formula. You're going to hear 4 formulas. Molecular, structural, line, and condensed. And hopefully, depending on how much progress we make today, I'll get chapter 10 homework in your hands, and we'll do one of the. We'll do one. We've got your first assignment right here has about 7 or 8 compounds, butane, etc. Gives you the name of the compound, and it says, okay, draw the condensed formula, the structural formula, the line formula. And then it continues over on the second page with 2 more. So your very first question, 12 points of this homework assignment, is filling out these three formulas for these 7 different compounds. Okay? So I'll get these in your hands. Not right now. You'll get too enamored by it. I'll give them to you hopefully before we leave, and we'll do one. We'll actually pick one and do all 3 of those so you go out of here and you kind of know what we're talking about. But let's look at this CnH2n plus 2. See what we're talking about. Propane is C3H8. Octane, now this is an octane rating, but if we were actually talking about octane, how many carbons do you think it would have? 8. Now let's take, so N is 8. N equals 8. 2 times 8 plus 2, 18. So octane is C8H18. Okay, that's what we mean by the general formula of an alkane. For the alkanes that are strung along in a chain, they're not in a ring, so we'll see that this applies to only when they're open chain. The bonds in alkanes have a tetrahedral structure with bond angles of 109.5 degrees. I'm usually a pretty talkative person, but I have been off all summer, and I'm not used to talking as much as I've been talking the last few days. And I'm starting to lose my voice.
Can you remind me what a tetrahedral looks like?
Oh my, Whitney. Bingo.
Just want to make sure.
You would think I've been feeding her the questions. Tetrahedral. 4 things. So if we looked at this thing, this has 4 faces to it. There's 1, 2, 3, and the bottom. All right, this is a 3-dimensional solid structure. I mean, that's what a tetrahedron is. You went over to Juniper Hall, to the math department, and was in geometry and studying tetrahedrons. You were studying cubes, rectangular solid, right? They tell you this is what it is. Here's what a cube is. Here's what a triangle is. They'd be in the geometry of it. This is what a tetrahedron would look like, and the carbon is at the center of that tetrahedron. A bond angle. You need to be talking about 3 atoms to define a bond angle. And remember, a line is defined by 2 points. So that hydrogen and that carbon only define a line. This hydrogen and this carbon defines another line, and the relationship of those 2 lines is a certain angle. 109.5 degree angle. 109.5 degree angle. 109.5 degree angle. Every one of these is a 109.5 degree angle because the carbon is sitting right at the center of the tetrahedron. So you're drawing lines out to the 4 corners of the tetrahedron. This is a model of methane. Remember from what I said on Monday, this isn't methane. It's a neat little kit we have that puts it together. They got these carbons drilled with the holes on them exactly at these angles. The molecule has nothing between the carbon and the hydrogen but a force of attraction. So, I mean, it would be more accurate if I was an octopus. I could do it. I could sit here, hold the carbon, and hold all 4 of the hydrogens around it and just say this is where we are. This hydrogen is attracted to that carbon, and it actually does vibrate. That chemical bond kind of vibrates a little bit. Hotter you get it, the more it vibrates. The colder you get it, the slower it vibrates. The closer they get together. But there is a vibrational energy in there, and I think that is in the microwave region of things that bond, that vibration. Yeah, good, Whitney. So that's methane. Let's look at these bond angles. All right, methane, ethane, propane, butane, pentane. You can see here we got octane, right? C8H18. We're using that general formula. Hexane, heptane, octane, nonane, decane. Down through to, I mean, we'll touch base with all of these, but we'll be in the lab and here's a bottle of hexane, or you'll see a bottle of cyclohexane. These names will be pretty routinely used. And let me cover one other thing I wanted to do. Well, we'll do it, this is a good time to do it. I'm going to give you each 3x5 card and then tell you that I'd like you to buy a package of 3x5 cards. I'll tell you what I want you to do with them. And you'll thank me as you're going into the final that you did. And you'll regret it if you don't do it. Right? But it'll be up to you. Yeah. Did everybody have one?
No, she didn't get it.
Who did? Okay, here's what I want you to do with these cards. And this is going to represent your first 10 cards. So you're going to have a card for each one of these. And let's take propane. Let's take propane. So here's what I would do with propane. Here's what I suggest you do with propane. So on the front of your card, write the name, propane. And then on the back of the card, put the structural formula of propane. Let me do that again over here. So propane, this here refers to one carbon. 2, 3, bute, 4, pent, like the pentagon. 5, hex, like a hexagon. Hept, an octagon, has 8 sides. Nonane, 9, the number of carbons that are in the molecule. So I see this name, propane, prop. And the very first thing it tells me is there are 3 carbons. So I put 3 carbons together. Ane tells me there are no double or triple bonds. So I don't put any double or triple bonds in here. It is a carbon, an organic carbon-based molecule. So the carbon has to have 4 bonds around it, one way, shape, or form. So this one only has 1. So I'm going to finish it off with hydrogens. And I've got 4 bonds around it. This carbon has 2 bonds on it already. It can only bond with 2 more things, 2 more hydrogens. And this carbon has 1 bond here, and now it has 4 bonds around it. 3 of them are hydrogens. Okay?
And the ane means it's only a single bond, right?
Ane means it is an alkane, which means it is a saturated hydrocarbon, which means there are only single bonds around the carbon. 4 of them. All right, so when you leave here today, go to the bookstore or somewhere, or go to Walmart, whatever, get some 3x5 cards, and chapter by chapter, you will be adding to your deck of cards. This is your first 10 cards. We'll start talking about some other things in Chapter 10, and you'll add at least 6 more, 6, 7, 8 more cards in Chapter 10. Chapter 10 probably will have the most cards. From now on, we'll go to Chapter 11. I'll say, well, you need a card for these molecules. You need a card for these molecules. Yes, Gabriel?
I was going to ask, do they have to be 3 by 5?
No, they can be 5 by 7. It can be whatever size you want them to be. These, you're never going to turn these in. These are for you to learn the molecules that I think you should know, and that I will potentially ask you to draw on the final exam, on exam 1, on the quiz. I may ask you to draw these molecules, or I may give you a drawing of the molecule and ask you to tell me what its name is. Okay? This course isn't going to be total memorization, but there's a certain amount of material that you have to be so comfortable with that you're not tripping over it trying to understand what comes next. Okay? All right, so let's move on. Those are there are many more alkanes than this, but these are teaching you 2 things. That the suffix is telling you what organic class it belongs to, and the prefix is telling you how many carbons are in the molecule. So they're talking here about Lewis dot and condensed formulas for methane or ethane. This is methane here, and this is ethane here. Just keep in mind a little reminder from 1305. Carbon is sitting right there. It's in group 4A. It has 4 valence electrons. And what do most atoms want around them? How many electrons? 8. So in order to get 8, it doesn't have 8, it only has 4 in the outer shell. It needs to share an electron with each of 4 hydrogens. This is why there are 4 bonds around carbons, not 5. It doesn't want 10 electrons around it, it wants 8. What gets 8, it's done. So that's what it wants. And so then we take that and we draw a line to represent 2 shared electrons, a covalent bond. So that's what that line is representing for us. And so that is the structural formula. It's basically saying, what is it? It's not showing the shape, it's just showing the 5 atoms and how they're associated with each other. So I'm not trying to do an artistic drawing of this thing, but just the structure. What is bound to what? We got that. This is a molecular formula. Just what elements are in there and how many of each. Doesn't tell us clearly how they are bonded to each other. And it gets real confusing. So this is of limited use. We will use it in this kind of a reaction. We will use the molecular formula. That's the most we'll do. If you want to put your molecular formulas here, feel free. C3H8. You could if you want to, but just that's a molecular formula. Get real familiar with the structural. All right, if we went up into, so there's okay, you can see that there's the methane. Here is actually propane. Now look, I drew that like it's straight. It's bent. It's not straight. We'll talk about that in a little bit. These rotate around these single bonds. That's propane. Why is that? Because, well, that's a 109.5 degree angle right there. It's not a 180 degree angle. That's what I got drawn there. But this isn't trying to accurately depict the shape. It's trying to accurately depict the 3 carbons and the 8 hydrogens and where are they bonded. You will never see, so don't ever do this, you're never going to see this sort of thing. You'll never see a hydrogen sticking there between 2 atoms. Why? This is hydrogen. It has 1 valence electron. It bonds to a carbon here, and it can't bond to anything else. It doesn't have anything to share with anybody else. So hydrogens are always on the end. They're never in the middle. Okay? So you're never going to find a hydrogen in the middle of 2 atoms. I should be careful saying never. But you never will. All right? You do. It's a misprint. So there's propane. This is the structural formula. This is a little bit confusing. This is a condensed formula, but I'll tell you what, let's see if we can get that out of there. I need to turn it black. But at any rate, a condensed formula would just be just this. CH3, CH2, CH3. Let me show you how the condensed works. Look right here. So what do we got right here? We have a carbon with 3 hydrogens around it. And what do we have right there? We have a carbon with 2 hydrogens around it. And then over here, the 3rd carbon is a CH3. So this is the condensed formula. If you were typing up a technical report in Word, you know, you'd be poking around trying to find these lines and trying to see how to get this in your paper. You would use a condensed formula, or could. You could use a condensed formula. This is kind of a hybrid between the two, so my apologies. This was an image that was cut and pasted out of something, and maybe even out of the book. And it doesn't need those lines. All right, so Lewis dot structure, we almost never use. We convert the 2 shared electrons into a line, and we have a structural formula. I just showed you the condensed formula. What's the line formula? Line formula. Line formula says, let's focus on the carbons and ignore the hydrogens. So it says let's look at the carbon backbone of the molecule and draw that as a line formula, or what you call in here line diagram, a line formula. And here's your propane. All right, so we're looking right there. So there's propane. You don't write any C's, you don't write any H's. You say, man, I like that already. Let's do pentane. Now let me explain something, because this is what some people get wrong. Well, let me show you how we're going to do this. Pentane, when you put your pencil on the paper, don't move it, just ching, that's 1. That's 1. So I put my pen on the paper here and I go 1, 2, 3, 4, 5. That's pentane. All right, where did I start with 1? Right there. The most common mistake that students will make is they'll go 1, 2, 3, 4, 5. And they've just drawn hexane, not pentane. They go 1. They get ahead of themselves. So when your pencil touches the paper, that's number 1. And then you start drawing. Because really, ethane is really boring. Boom. It's ethane. Okay, the other thing is that propane is not just a longer line. It's got to have a bend in it. It's got to have a bend in it. If you drew that on your paper for propane, I'd say, no, that's not propane, that's ethane. I only see 1, 2. I don't care how long the line is. There was no bend in it. So for the alkanes, every time you get to another carbon, you bend. You bend. This is hexane. And this is pentane. Okay?
So for ethane, it's like a little bend. Like a little bit?
No, there's no bend. That's a straight line.
Okay.
Sorry. It's got a little arc to it. I'm just straight line. Use a ruler, whatever. There's no bend in that.
What would be methane?
Right here.
Okay, there's methane. We don't talk about a line formula for methane, okay? That's methane. It's just a dot. 1 carbon sitting there. And see, everything else you will have, everything else I just taught you about saturated hydrocarbons tells you there has to be 4 bonds around every carbon. So if I looked at that carbon and I said, well, it's got a carbon over here, it's got a carbon over here, so it really only has 2 hydrogens. And yet this carbon here has only 1 carbon on it, and it has 1, 2, 3 hydrogens on it. So the line formula, I can construct a structural formula from a line formula, knowing the behavior of carbon. Okay, here's a condensed formula. Here's a little bit more complicated molecule. It's not very complicated, but a little bit more complicated. So we got 1, 2, 3, 4, 5 carbons here. We've got a side chain, another carbon coming off of the side, CH3 group, on the second carbon. On the third carbon, we have a hydrogen, and we have a chlorine here. This is what we would call, this is one of these alkyl halides. It is a chloride, or chloro. This is a chloro compound. It's got a chlorine on it. All right, so there's the structural formula of that molecule. And what we're doing down here, and this is good because it doesn't have any bonds in here. This is a good condensed formula. So this is the condensed. And sometimes it's good to just draw them right underneath so that you can see. Here's the first carbon, here is the second carbon, here is the third carbon, the fourth carbon, and the fifth carbon. Okay? So what do we have on the end? We have a CH3. Here's our second carbon. It has a hydrogen, and it also has a CH3 group on it. And we put that in parentheses.
So for side chains, would you always use parentheses?
Yeah. You'd put the side chain in a parenthesis. I don't need to put these hydrogens. It's a hydrogen. They are just a single entity. It's just a hydrogen. But this is not a single entity. It is a group up there of 4 atoms. So I put parentheses around that whole group. And where is it? I come to this carbon, and I know it's in the middle of this chain, so it has to have 2 things on it. What are those 2 things? A hydrogen and a CH3. That's exactly what's on there. I come to the third carbon. It has a hydrogen and it has a chloro. I'm not putting that in parentheses because that is just one thing. It's not a carbon. It is a chlorine atom, or it's a chloro group. And then CH2 and CH3. All right. This is fundamental to the rest of the 5 chapters. IUPAC names. The IUPAC naming system. It stands for the International Union of Pure and Applied Chemistry. It's an international committee. Someone in San Antonio develops a new drug. It's a new, really elegant molecule with this over here and that over there and different functional groups here and there. It's an organic molecule. They would submit it to IUPAC and say, this is the name we would, given the IUPAC systematic way of naming molecules, this is what we think should be the name. And IUPAC would officially stamp that. This is going to be the name of that molecule. Okay? So it's a clearinghouse for not getting confused about things. Because early on in organic chemistry, people were naming molecules, they were given common names to these molecules. And people in London couldn't talk to people in Munich and couldn't talk to people in New York or Moscow. They didn't know what molecules they were talking about because there wasn't a systematic way of naming them. So this was developed early 1900s and ever since has been the clearinghouse. And there's 6 rules, 6 systematic rules you apply. Not necessarily name a real complicated pharmaceutical, but common organic molecules. We're going to learn these 6 rules, and it'll help you name a whole lot of molecules, or from the name be able to draw them. But before we do that, let me go back to this slide. Before we do that, we have to learn the names of some side groups that are very common on organic molecules. This is probably the most common. CH3 group. Now let me go, okay, the CH3 group. If you think about it, this is methane. It's not a CH3 group, it's a CH4 molecule. It's a molecule. But if I were to take one of those hydrogens off and leave a place where this group could be attached to a carbon, any carbon, on any molecule, we're going to not call it methane, but we are going to call it meth. There's only one carbon in this group. Methyl. YL. That is a methyl group. So we go back to that molecule we were looking at. That would have been a 5-carbon organic molecule with a methyl group on the second carbon. So we went to name it. We weren't ready to talk about how to name that molecule. We would call that a methyl something, methylpentane, 2-methylpentane. So methane becomes methyl. And whenever you see this YL, it's going to be a group. So you're going to need 6 of these. And there's your first one. So as these come along, I suggest you have one for the methyl group. Methyl. One carbon with 1 carbon with 3 hydrogens and an open position where it can attach to an organic molecule of some sort. Ethyl. So if you took ethane and dropped off one of the hydrogens, you'd have an ethyl group. Okay, I'm going to be happy with that. I don't want to dig into IUPAC much more, but you've seen how far we've gotten. Talked about alkanes. We talked about the general formula of alkanes. Talked about the general bonding, what does it mean to have a saturated carbon with 4 single bonds around it. You're learning that the suffix tells you what class it belongs to. The prefix of the name tells you how many carbons it has. We're going to, on Monday, what is today? Wednesday, Monday, we will go through all... Today's Wednesday?
No, Monday's Labor Day.
Ah, Monday's Labor Day. Thank you. Oh, good. I might have driven all the way over here.
I would have been here with you. Told me at the beginning.
Okay. Okay. So Monday's Labor Day. Wednesday. Okay, I was wondering, what are you telling me? Wednesday. Right. So Wednesday we will dig into IUPAC. Don't leave yet, because I want to get this Chapter 10 homework in your hands. And we'll pick up right here